Hey class, Mr. Modian here with a video on the proof of the fundamental theorem of calculus. I looked for a good video online, and there's some really good ones out there that cover a lot of detail and a lot of very intricate math, but might get in the way of the geometric approach that we used, so I figured I'd make a quick video illustrating what we did in sort of a pause yourself or pace yourself sort of context where you can watch it at a more comfortable leisure. So let's go ahead and take a look. Our goal is to show that this statement is true. Now what is it saying? It's saying that the derivative of an accumulation function, which is what this thing here is the function you are accumulating underneath. Or, effectively, that these two operations are inverses of each other and as such will cancel, and what you're left with is the function underneath or inside. So let's go ahead and look at a graph. So here we have a t-axis, a horizontal axis, and we have a function of those t values called g of t, just an arbitrary continuous function. X is a t value, and x can live anywhere on this t-axis, and from where I have x right now, it is a bit more than some arbitrary number a, which is a fixed point on the t-axis. So, for example, right now x sort of basically is whatever this number is, and when I create this line here, it sort of creates this region, right? And as x changes, if I make x bigger, it would change and make a bigger region. If I make x smaller, it would change and make a smaller region. But essentially, the value of x dictates a region, an area of a region underneath this g of t curve. So in order to investigate these areas further, I'm going to make sort of a secondary function, another function, based on these areas. So I'm going to define, so let f of x, new function, and the definition of this function, the way in which it is created, notice that it's based on x values, not t values, although x is sort of a domain of t. We're in the domain of t. F of x is going to be the area under the curve from a up to whatever my changing x is underneath g of t dt. So as I was illustrating earlier, if I made x bigger, f of x would also grow to be a bigger area, and if I had made x smaller, f of x would shrink to give a smaller area of a smaller region. So we're looking for, oops, this should actually be dt. We're basically looking for what can we find from this function. We don't see a graph of f, but what can we infer or determine about f despite not having a graph thereof? As is often the case in calculus, we're going to investigate what happens when you change this function just a little bit. So I made these sort of large changes. If I move this here, I get a bigger space. If I move this here, I get a much smaller space over here. If I just nudge this function just a little bit, what's going to happen in that change? So I've exaggerated the change here quite a bit just to make it visible, but in theory, this delta x is meant to be quite small. So if I make this small little nudge, and I create a larger region, again, which I've blown up here, we can consider that the size of that nudge, delta x, to be some arbitrary number, and that creates a new t value called x plus delta x, which is further down on the t-axis, right? And let's investigate this new amount of space that just sort of came into being, because before, f of x represents the amount of space right here, right? So this new part just sort of came into being. So let's think about how we can express the size of this region. Now, from the way I've drawn it, it certainly looks a lot like a rectangle. Keep in mind that this is curved, so it's not exactly a rectangle, although my drawing is a little suspiciously linear here. But in theory, it could be certainly approximated by a rectangle. So how do we estimate this area? Well, this area is approximately equal to the area of the rectangle that sort of is closely modeling or defining this space. So the area of a rectangle is base times height, and the base would be this width, which is the same as delta x. So delta x times the height, which is, one might say, a y value. Well, here that's a little bit of a misnomer since there's no x-y axis, it's a t-axis, but some sort of output of a function. And the height of this part of the curve, of course, is dependent upon what the input is, and the output would be g of t. So basically, the height here is going to be g of some t value, and since we're in the x region, let's call it g of x. Now, strictly speaking, g of x is the height of this part of the rectangle, and since this is an approximation, the real height of this portion would be g of x plus delta x. But for simplicity's sake, let's just call it g of x. We're going to shrink delta x in a moment anyway. So long story short, this height right here is pretty close to g of x. Since order does not matter when you multiply, I'm just going to write this in a more familiar form. I'm going to write this as g of x height times delta x base. That's one way to represent the area of the red little sliver, this little strip that just popped out. We're going to look at that same sliver in a different representation. So this is what we already had from the last slide, right? Since this area in red is essentially the difference between this area here in blue, so that blue space, which is obviously much bigger than my red space, but if I remove here in, let's say, orange, if I remove this chunk, blue minus orange will give me the red space that I want. So another way of expressing the same thing, two different approaches to the same space. This space can be expressed as, in color terms, blue stuff minus orange stuff. Now let's formalize it a bit. The area, the amount of blue that we see here, well, that's going to be an output of our secondary function that we created, f, right? Let me go back a few slides. Remember, f is defined to be the area from a up to whatever number you want underneath g of t. So since my blue function stops at x plus delta x, my blue space essentially is the area from a to x plus delta x underneath g of t, which is dt, which is a convoluted way of saying essentially f, which is my function that this is based, or that is defined like this, f of x plus delta x. And likewise, my orange space, I'll just go ahead and skip this intermediate step, it's not really needed. The orange space is the area from a up to this x, right? And that's defined as our area function f up to x. So another way of expressing the red space is the area of the blue, which is f of x plus delta x, minus the area of the orange, which is just f all the way up to x, or f of x, which is a up to x. So these two things essentially are describing the same thing, and as such, we can set them equal to each other. So the area of that little sliver as a rectangle is this, and as the difference between two sort of areas under the curve, which is what the definition of f is made to be here, would be that portion over there. I'm going to divide both sides by delta x. Delta x is a non-zero value at the moment. It's a little nudge. Divide both sides by it, and that will give me g of x is equal to f of x plus delta x minus f of x over delta x. So we now have g of x all by itself, right? That's interesting. Now keep in mind, delta x represents the size of our nudge, right? Which I've exaggerated here to make it more visible. Really what we're interested in, really in calculus as a whole, but here in particular, is how does this function behave? How does this relationship change when you change the input just a little bit? In other words, when delta x is really tiny, how does that, what kind of changes does that yield? Is it a large change? Is it a very small change, just like the input? What's the relationship between input and output, right? So essentially, let's concern ourselves not with delta x as is, but rather with delta x approaching 0. So what happens when delta x is really small? So the limit as delta x approaches 0 will essentially shrink the size of our nudge to infinitely small values. And here is where some alarm bells might be going off. Because this thing right here, if you recall from roughly September in our calculus curriculum, this is the definition of derivative, the limit definition of derivative, which is the difference quotient, which is this guy right here, change in y values or outputs over the change in inputs as the change in inputs shrinks to 0, which essentially gives you 0 over 0, but as we learned in limits back in August, you can massage these things and make meaningful math come out of 0 over 0, because that's an indeterminate form. So this is the definition of derivative, and if you look, this is exactly what we have on the right-hand side. And as such, I can replace this entire portion with the derivative of f. So now, on the other side of the equation, on the left-hand side, notice that this is delta x approaches 0. There's no delta x in this thing, so I can shrink delta x all I want. It's still going to be g of x, because there's no delta x impacting g of x. So now we have this, that g of x is equal to f prime of x. We're almost there. So let me go ahead and get some new space here. Oops. So we're at this stage right here. G of x is equal to f prime of x. I'm going to switch these things around. It's something I didn't do in class, but I think it's a more useful demonstration here. I'm going to use an alternate representation of the derivative. I'm going to write this as the derivative with respect to x of f of x. Another way of saying the same thing, as is often the case in math. The reason I did that is I can now replace f of x with what I defined it as several pages ago. We remember the definition of f, which we created as a secondary function, effectively was this: the area under the curve from a up to whatever number x we're dealing with of underneath g of t dt. So that's what f is equal to, right? So I'm just replacing it with the definition, is equal to g of x. And right away you have the result that I started the video with. That effectively this operation of taking the derivative and this operation of taking a definite integral are opposites of each other, and as such you're basically just left with the function in question. So the actual statement of the fundamental theorem of calculus, part 1, as most people define it to be, is this right here. If you have a function which is the accumulation of area underneath some other function, then the derivative of that accumulation function is simply the function itself. When you take the derivative of both sides here, you just plop x in its place, you have t, and there's your answer. Alright, hope this helps.